In this video, we'll discuss how a shape optimization study can be used to lightweight a design. In many applications, parts are over-designed for a variety of reasons, including lacking time or additional cost for manufacturing. With 3D printing becoming a viable manufacturing technology, reducing material used reduces production time and material costs. Here, we see the resulting mesh generated by the shape optimization study for a robot gripper arm. Let's take a step back and review what is required to set up and run this study. We've got our original geometry, known as the build envelope, which is made of steel. As we enter the simulation workspace, we are prompted to create a new study. We will select Shape Optimization and click OK. We can apply or change materials if they were not assigned properly in the modeling workspace. Now, we can constrain the model using two pin constraints. The pin constraints limit both radial and axial movement along the two selected surfaces. Next, we can apply a load at the location we expect the gripper arm to experience a force. We'll use a 500 Newton compressive load to the surface of the gripper arm. These types of compressive forces are what the part is designed to handle from design criteria. It is worth noting that a load of 1 could be used here, as the shape optimization study does not take stress into account. To ensure that your newly designed part is adequate for your design criteria, you should also run a static stress study to validate your design. For this example, we want to keep the material surrounding the pinholes intact so that the connection functions as expected. To do so, we'll use the Preserve Region feature to hide this portion of the model from the shape optimization routine. Since this gripper arm is symmetric about the thickness, we can utilize a symmetry plane. The symmetry plane has two effects. First, to force the optimized shape to be symmetrical, and second, to speed up the solution time. We can adjust the criteria for the study. We want to produce a shape that is roughly 40% of the original mass while maximizing the stiffness of the part. Before solving, we need to adjust the mesh criteria from the settings dialog. Generally speaking, the more we refine the mesh, the closer the solution can get to this objective. At last, we can solve the model in the cloud and produce the optimized shape. Results appear as soon as the solution is finished and the results are downloaded from the cloud. We can manipulate the mass percentage to get a reasonable result. Now what? We want to further investigate and finish off our new design. So, we promote the mesh, which brings it back to the modeling workspace. Then, we'll make some changes to the geometry using the standard modeling tools. We don't want to follow the mesh too closely. We're just trying to remove the material from the original build envelope using the mesh as a guide. Then, we can bring it back into simulation and do a static stress study to validate we didn't remove too much from the design. I already ran the analysis here. As you can see, my safety factor is only 1.74, which means if there are any flaws in the material, which is likely if it was printed, or even a quickly applied load could cause failure. When using the shape optimization study, it is important that you validate your design using the other study types as well. I hope this helps. Happy simulating!